and we move on to wind loads. But of course, we will not talk about those in detail here in the lecture. I will leave this up for you for practice, but I want to give you some pointers and hints here. So what you will see is that we have wind load that is slightly different than the cases we dealt with before. And that is because we now dealing with a windward side. So this here would be windward side, and this would be the lee side, or the side that is, you know, against, or like that's under wind suction, if you will. And so you have wind very perfectly perpendicular to the axis of the beam on both sides, but one is pushing on the roof, the other one is pulling on the roof. And this is very typical for wind loads. Of course, it depends highly on the pitch of the roof, but you have wind pushing in on one side and pulling on the other side. And so this is not a symmetric system anymore. It's a little bit more challenging, but also a little bit easier, because now all your forces are actually 100% perpendicular to the axis of the beam. So there's no parallel component actually in this case. So that should make the life a little bit easier. Wind, similar to snow loads, is actually defined per geographic regions. In ASCE 7 is the document that defines wind. This is past or beyond the purpose of this class, but based on the geographic region, it tells you how much wind pressure you have and wind suction. Of course, again, it's also dependent on the geometry of the roof, which goes way beyond the purpose of this lecture. But just so you know, that is defined somewhere else. For the purpose of this educational analysis, we're also going to make this here 500 Newton per meter, and we'll make it also 500 Newton per meter on the other side, which would never be the case, or very rarely be the case, that the windward side and the leeward side is identical to each other. But this will make your life a little bit easier. And I will now shy away from solving this for you, but you would first have to calculate your support reactions yourself, right? So you still have the 4 support reactions. Then you would have to break them down. And then, of course, you go through the very same exercise. You define your function n of x, your v of x, and your m of x. And be a little bit careful here, because maybe the left side is different than the right side in this case. But ultimately, you can draw your diagrams, and that is the part that I already have done for you. So you see here the normal force is actually a constant in this case, and I'll let you study that, why that is and how that is. And the shear force diagram now, so maybe I'll include that for you, the information that this is shear force and this is in kilonewton. Then this here is the normal force, and this is also in kilonewton. And then we have the moment diagram. And notice that the system actually in this case was anti-symmetric. Actually symmetric, and the load case was anti-symmetric. And what that means is that your shear force diagram actually happens to be symmetric in this case. So this is a symmetric shear function or shear diagram. And your moment diagram is actually anti-symmetric in this case. The normal core force is not really affected by this, except, of course, due to the support reaction and the pitch. There's like an initial value here, but because all the forces are acting perpendicular to the roof, there's no increase or decrease in normal force. And you see the values are given here to you, so you already have the answers. Now it's up to you to really calculate how to get these values and how to reach those diagrams.